Now you might ask, when would you want to change into polar coordinates? Usually it's because we want to simplify the description of our integration region D. Sometimes we might want to simplify F. Now let's take a look at an example of this. So let's say we integrate 4 minus x squared minus y squared dA, and this is our region of integration given to us in Cartesian coordinates. Based on the description here, this region of integration turns out to be this semicircle, and it's everything inside there. In polar coordinates, what we've got is a circle that goes from 0 to 2 in radius, also going from negative pi over 2 to positive pi over 2 in angle. So it's quite straightforward to describe it there. The other thing that happens very nicely is that this is the same as subtracting r squared. If we want to integrate this function in polar coordinates, it turns out to have a relatively simple description. Remember, the angular integral is always second, the radial integral is always first. The function that we've got is 4 minus r squared, and now we have to put in this area distortion factor. This can be done with a simple substitution. U is 4 minus r squared, du will then be negative 2r dr. Very luckily or conveniently for us, we have a factor of r dr present. R is 0 becoming u is 4. R is 2 becoming u is 0. An integral from 4 to 0, u to the 1/2 du over negative 2, followed by this theta integral. The presence of the negative sign allows me to flip the limits of integration by our standard integration properties. We'll have an integral 0 to 4, u to the 1/2. This 1/2 comes out front. That's that area distortion factor. Simple power rule for antiderivatives. What we'll have is u to the 3/2 over 3/2. We'll have this 1/2 out front. This is evaluated from 0 to 4. The 1/2 and the 3/2 will cancel to give me a 1/3. Then I'll have 4 to the 3/2 minus 0 to the 3/2 d theta. This is like the square root of 4 cubed, which is 8. So I'll have a 1/3 integral from negative pi over 2 to positive pi over 2, 8 d theta. So this gives me 8/3 pi over 2 minus negative pi over 2, which is 8 pi over 3. As an example of something more involved, let's find the area of the region inside the circle for sine theta is r, and outside the circle, r is equal to 2. Now note, if we want to find the area of a region, this can be done simply by taking the double integral of the function 1. This was an integration property. Now another note, just to try to help us visualize this, if we had r is 4 sine theta, remember that sine theta is y over r. So this gives us an r squared is 4y, x squared plus y squared is 4y, x squared plus y squared minus 4y is 0. If we were to complete the square, what we would need to do would be to add a term 4 on both sides. This would give us y minus 2 squared is 4. So this is a circle that has a radius of 2 and a center of 0 and 2. So the integration region here looks like the following. We've got r equals 2 is a circle of radius 2, so that looks like this. There's r equals 2. This other circle has a center of 0 and 2 and a radius of 2. So it looks something like this. And what we are doing is trying to integrate this along some angular region where those two curves intersect. So this would be some angle theta alpha, and theta is beta. And the region of integration that we are interested in is this region right here, inside the blue curve but outside the white curve. To figure out the intersection points, what we have to do is set r equals 2 to r equals 4 sine theta. This tells us that sine theta is a half. This happens when the angle is in quadrant 1 and in quadrant 2. As we're seeing, sine is positive in there. The reference angle is pi over 6 is the solution, and the quadrant 2 answer would be 5 pi over 6. So the limits of integration here would be constant in the theta direction, but in the radial direction, we would have the following. So the area is simply an integral as follows. We have our 1 is the function, and then we have to make sure we contain the proper area distortion factor here. So now it's just a process of going through and working through this function. We'll have an r squared over 2 evaluated from 2 to 4 sine theta. We'll have a 1/2 factor coming out front. We'll have 4 sine theta squared minus 2 squared d theta. This will give us a 16 sine theta squared minus 4. This factor of a half can be brought inside to simplify all these results. After we go through the simplification, there will be a common factor of 2, and I'll be left with 4 sine squared theta minus 1 d theta. There's a trig identity that allows us to integrate this. Sine squared theta is a half of 1 minus cosine 2 theta. I can simplify everything as follows. I'll get that factor of 2 out front. I'll now have a 4 over 2, 1 minus cos 2 theta, subtract a 1. This will give me a 2. I'll get a 2 minus 2 cos 2 theta, subtract 1. This will end up giving me a 2 pi over 6 into 5 pi over 6. I'll have a 1 minus 2 cos 2 theta. You can split this up into 2 separate integrals. We'll have a d theta, subtract a 4 pi by 6 into 5 pi by 6, cosine of 2 theta d theta. Substitution here, u would be 2 theta, du would be 2 d theta. When theta is pi over 6, u is pi over 3. When theta is 5 pi over 6, u is 5 pi over 3. This ends up giving me 5 pi over 6 minus pi over 6 in that first integral. 4 over 2. I'll now have pi by 3 to 5 pi over 3 cosine of u du. This is going to be 2 into 4 pi over 6 minus 2. The antiderivative of cos is sine. This will be 4 pi over 3. Subtract 2 into sine of 5 pi over 3. Subtract the sine of pi over 3. 5 pi over 3 lives in quadrant 4. And so that means that the sine is a negative value. The reference angle is root 3 over 2. So this would be negative root 3 over 2. This ends up giving me a 4 pi over 3 plus 2 into 2 bunches of root 3 over 2. Those go away, so at the end of the day, this will be 4 pi over 3 plus 2 bunches of root 3.